Welcome to the session on algebraic methods, methods of proof. The objectives for this session are to construct a sound mathematical proof and disprove a mathematical statement using a counterexample. A mathematical statement can be proved by exhaustion. This involves breaking the statement into smaller cases and proving each part separately. This is suited to small results. One example cannot prove a statement on its own. So let's take a look at an example. We would like to prove that the sum of any two consecutive square numbers between 1 and 25 is odd. Pause the video and have a go. Press play when you're ready to view the solution. So let's solve this. The square numbers between 1 and 25 are the following: 1, which is 1 squared, 4, which is 2 squared, 9, which is 3 squared, 16, which is 4 squared, and 25, which is 5 squared. Clearly, this is a finite number of numbers. So let's add consecutive numbers. 1 add 4 is 5. 4 add 9 is 13. 9 add 16 is 25. And 16 add 25 is 41. Notice that all these numbers are odd. Therefore, the sum of any two consecutive square numbers between 1 and 25 is odd. Let's take a look at another example. Prove that all cube numbers are either a multiple of 9 or one more or one less than a multiple of 9. Pause the video and have a go. Press play when you're ready to view the solution. So let's solve this. Now all cube numbers take the form 3n all cubed, or 3n plus 1 all cubed, or 3n plus 2 all cubed, where n is a natural number. Why is this the case? Let's consider 3n plus 3 all cubed. Can we write it in any of the above forms? 3n plus 3 all cubed can be rewritten as 3 times n plus 1 all cubed. But notice that this is the same as saying 3m all cubed, where m is equal to another natural number, n plus 1. In particular, we're saying that 3n all cubed and 3m all cubed are in the same format. Similarly, we can show this for the other cases, namely 3n plus 4 all cubed and 3n plus 5 all cubed. Have a go yourself. And so we have reassured ourselves that all cube numbers take the form 3n all cubed, or 3n plus 1 all cubed, or 3n plus 2 all cubed, for n a natural number. Let's now take a look at 3n all cubed. This equals 27n cubed, which equals 9 times 3n cubed, which is clearly a multiple of 9. Now let's take a look at 3n plus 1 all cubed. This equals, once we've expanded, 27n cubed plus 27n squared plus 9n plus 1. And if we factorize it in the form we want, which is 9 times a whole number plus 1, then we can show that this is actually of the form 9 times something plus 1 more. So this is a number which is a multiple of 9 plus 1. Now let's consider 3n plus 2 all cubed, which equals 27n cubed plus 54n squared plus 36n plus 8 once we've expanded. This in turn equals 9 times something minus 1, and therefore we have it in the form a multiple of 9 minus 1, as shown. And therefore, all cubed numbers are either a multiple of 9 or one more or one less than a multiple of 9. Let's now take a look at how we can disprove a mathematical statement. So a mathematical statement can be disproved by using a counterexample. A counterexample is one example which does not work for the statement. Let's take a look at an example. Prove that the following statement is not true. The sum of two prime numbers is always even. Pause the video and have a go. Press play when you're ready to view the solution. So let's solve this. Let's take the case of two prime numbers, 2 and 3. Clearly 2 plus 3 equals 5. However, both numbers 2 and 3 are prime. However, their sum is odd. We do not need another counterexample to disprove this statement. Let's take a look at another example. Example 4 part A asks you to prove that for all positive x and y, x over y plus y over x is greater than or equal to 2. And part B asks you to show that this is not true when x and y are not both positive. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve this. We're going to begin by doing some rough working for example 4a. Let's work backwards. Here's the statement. It implies, if we have xy as a common denominator, that x squared plus y squared all over xy is greater than or equal to 2. And finally, when we rearrange, then we obtain x minus y all squared is greater than or equal to 0. Now clearly we know that x minus y all squared is greater than or equal to 0. So we can use that as a starting point for our formal proof. So let's have a look at how we can present this formally. We're going to solve this. Let's consider x minus y all squared. We know that x minus y all squared is greater than or equal to 0. So if we expand, we obtain x squared plus y squared minus 2xy is greater than or equal to 0. And then rearrange, put x squared plus y squared on one side and 2xy on the other. Now since x and y are both positive, x times y is also positive. So we can divide by xy without changing the sign around. So let's do that. And therefore we've obtained x over y plus y over x is greater than or equal to 2, which is what we were required to prove. Now part B asks us to show that this is not true when x and y are not both positive. Let's solve this. Let's try x equals minus 2 and y equals 3 in the equation. So we have x over y plus y over x is greater than or equal to 2. Substituting on the left-hand side gives us 5 over 6. But clearly 5 over 6 is not greater than or equal to 2. And therefore the statement is not true that x over y plus y over x is greater than or equal to 2 when x and y are not both positive. As you can see, one example is sufficient to disprove a statement. This brings us to the end of this session. If you have understood its contents, you should be able to construct a sound mathematical proof and disprove a mathematical statement using a counterexample. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.